Good afternoon. I'm Yishen Li from National Tsinghua University, Taiwan. I am on behalf of the second team, and now I'll introduce our mission, OCCC, Ocean Climate CubeSat Constellation. Climate change and extreme weather causes millions of casualties and trillions of financial loss from 1970 to 2019. A key factor of the aforementioned phenomenon is the ocean-atmosphere interaction, or abbreviated as the AO interactions, which is very complex and difficult to comprehend. As we can see in the picture, it is very complicated since the atmosphere and the ocean are a coupled system. Take physical interactions, for example, which our mission focuses on. The ocean transfers heat and moisture to the atmosphere. On the other hand, the atmosphere provides driving forces to ocean currents and changes sea surface temperature and ocean salinity. However, this system is poorly understood, and coupling is often ignored in existing weather models due to the insufficient data coverage provided by modern weather satellites. The only way to solve this problem is to have more data with higher coverage and accuracy. By doing so, we're more likely to understand the process of AO interactions and know how to deal with the climate crisis. The primary objective of our mission, OCCC, is to investigate the physical process of AO interactions and related weather disasters, such as tropical cyclones and heat waves. This coupled and complex system will require timely in situ measurements of dynamical properties of the ocean and the atmosphere simultaneously, including temperatures of the ocean and the atmosphere, ocean surface wind, and ocean aerosol. Take tropical cyclones as an example. Current weather models are capable of predicting the paths of tropical cyclones, yet the formation places of these tropical storms have been elusive. Our mission will be able to monitor the ocean and the atmosphere status throughout the lifetime of a cyclone. In addition, the vision of OCCC also matches 3 of the 17 Sustainable Development Goals of the United Nations, which are 11. Make cities and human settlements more inclusive, safe, resilient, and sustainable. 13. Take urgent action to combat climate change and its impacts. And 14. Conserve and sustainably use the oceans, seas, and marine resources for sustainable development. The mission will be implemented by a constellation of 16 CubeSats, lots of ground-based remote sensing platforms, and ground stations worldwide. The satellite is a custom 6U CubeSat with a mass of approximately 13.64 kilograms. OCCC's CubeSats will be composed of 6 subsystems and 4 scientific payloads, which are Global Navigation Satellite System Radio Occultation (GNSSRO), Global Navigation Satellite System Reflectometry (GNSSR), Spectrometer, and Internet of Things (IoT). Ground-based remote sensing platforms are designed for in situ measurements for calibration and assisting data. The platforms will include sounding balloons and buoys. Sounding balloons will use sounding balloons for atmospheric data and buoys for ocean data. The data will be transmitted by the IoT transmitter and collected by our space segment via the IoT receiver. We will employ a network of ground stations distributed globally in order to receive downlink data from the constellation in real time. The GNSSR payload is used to derive delayed Doppler maps to retrieve sea wind speed, sea surface height, and sea ice. These data are derived from the sea surface GNSS by static scattering. We can also obtain sea salinity by combining data with the radometer. We will require 13 dBi nadir LHCP L-band antennas, L-band radometers, as well as good computing power for onboard computing and large memory storage. The GNSSRO payload uses descending radio occultation to retrieve atmospheric temperature, moisture, and pressure of the troposphere by calculations done on a bending angle and impact index. We will require L1 and L2 dual bands, high-gain antennas 12.5 dBi, reliable clock sources, and computing modules. As for the spectrometer payload, we use visible and infrared radometer, VIRR. By observing the visible and near-infrared channels, we can derive sea surface temperature, SST, which is used for contrastive calculations of cloud and ocean sensitivities. We use algorithms and tools including multi-channel SST, MCSST, to derive the SST. The aerosol AOD wavelength coefficient algorithm is used to obtain ocean aerosol for atmospheric data correction. We use the difference of temperature between cloud bands to acquire the cloud data to mask the area with cloud coverage. Last, we have an IoT payload, which is a receiver to collect in situ data for calibration and onboard computing. We use long-range, abbreviated as LoRa, technology because it is capable of transmitting over long distances, consuming low power, and anti-Doppler. Our sensor network includes sounding balloons for atmospheric data and buoys for ocean data. Airplanes and ships are optional platforms. Now I'm going to explain the key performance factors in our mission. The first factor is the spatial resolution, which should be 1 kilometer for all collected data to study the AO interaction. The second factor is the time resolution. At 35° north latitude to 35° south latitude, we need a temporal resolution less than 12 hours for tropical cyclone prediction. The third factor is that the full ocean coverage should be achieved in a day for global weather models. Last, we plan the mission lifetime to be in 6 years for 1 year of calibration and 5 years of operation. As for the orbit of our satellites, since our mission is to observe global AO interaction, it requires global coverage of the ocean. Tropical cyclones usually occur at latitudes between 35° north and 35° south. Furthermore, according to the numerical models, 12 hours or less temporal resolution is required for cyclone weather prediction. Taking the ability of CubeSat orbiting into consideration, we separate the constellation into 4 launches, which are 4 orbit planes with 2 polar orbits and 2 low inclination orbits, 35° inclination. We can see from the picture that there is a green polar orbit and a blue one, and there's an orange low inclination orbit and a red one. The orbit height is 575 kilometers. The reason why we separate them into 4 orbit planes is that it is too hard for us to use propulsion to change the right ascension of the ascending node, RAAN. If we use 4 orbit planes, we can decrease the conditions in which we need to change the orbits. The constellation can achieve global ocean coverage in a day and access the cyclone occurrence area for 6 hours at a time. The OCCC project will be managed by the Taiwan Institute of Planetary Science and System Engineering, TIPSI. TIPSI are also responsible for system engineering. The Babui Aerospace team is responsible for the development of the CubeSat bus and the GNSSR payload. NCKU, National Cheng Kung University, will develop the spectrometer and GNSSRO payload. As for the IoT sensor platforms, we anticipate inviting NCKU, NCU, National Central University, and NTU, National Taiwan University to perform the sounding balloons. The Institute of Ocean Science from NCU and Academia Sinica have lots of experience with buoys, so they'll participate in the design and implementation process. We shall need ground stations to telecommand the satellite and telemetry science data as well, in which NCU and NCKU are experienced. Assuming that National Space Organization NSPO can provide help and communicate with its overseas ground stations, global data downloads can be achieved. There'll be multiple organizations and universities participating in data processing. The following is our budget for each CubeSat with details listed below. From building to launch, the total cost is estimated to be around $3,241,400 per CubeSat. For OCCC, we have 16 CubeSats to form a globally distributed constellation. We design mission phases as shown in the chart below. According to the NASA Space Flight Project Life Cycle and the NASA CubeSat Launch Initiative, the whole process takes about 9.5 years. Phase E, which starts from 2025 to 2031, 6 years in total, is our mission lifetime. That's all for our mission briefing. Thank you very much for your time, and we're happy to take questions or comments.